Hey guys, welcome back. We'll be finishing up our chapter on confidence intervals with answering this very practical question of choosing a sample size. So going back to our example of the sea fans that were infected with aspergillosis and the Lacertus reef in the Yucatan. So we randomly sampled 104 sea fans and we found 54 of those were infected. So from that we were able to create a confidence interval. So I'll show you how to do that real quick. So you go to stat, test, towards the bottom be 1 proportion z test. There were 54 infected out of 104. We can choose our confidence level. Usually we do 90%, 95, or 99%. The default is usually just to do 95%. Then we hit calculate, and this will give us our sample proportion. It'll calculate that for you, sample size, and then right here we have our confidence interval. So we'd interpret that by saying we're 95% confident that the true proportion of sea fans infected with aspergillosis and a Lacertus reef in the Yucatan is somewhere between roughly 42% and 62%. Now, if we look at that confidence interval, 95% of the time, we would successfully capture the true proportion. So it's probably going to be somewhere in between those two. But that's a pretty wide range. And so there's kind of this trade-off between precision and confidence. So if we want to have a smaller margin of error, because we're saying it's basically about between plus or minus 10%, which is 20% range altogether. That's not very precise. So we would need to do a few things to make it more precise. Either we lose a degree of certainty by decreasing it to 90% confidence level. So I could run that real quick for you because the calculator's doing it. Oops, didn't want to do that. Let's try this again. So stat test, we'll do 1 proportion z test. I'm going to do the exact same thing, but now I'm going to go down to just 90% confidence. We usually don't go below 90%. Okay, so now we're between roughly 44 and 60%. So that's about an 8% margin of error. So plus or minus 8%, which is less than 10%, but now we're going to be wrong 10% of the time because it's only 90% confidence. So without losing amount of confidence, we want to increase our precision. The only way we can do that is actually by increasing our sample size. So the question is going to be asked, if we're starting out our study and we want to narrow it in with a certain level of confidence within a margin of error, let's say instead of 10%, we want a margin of error of 5%. So basically, what sample size would we need? So before we ever put on our scuba gear and go down and sample these sea fans, we would actually want to answer the question of, well, how many sea fans would we have to be able to sample in order to get it to a certain precision with a certain level of confidence? And before we ever go diving, we would actually want to answer that question to make sure we have enough money or to go back and ask for more money for whatever research we're doing, whoever's footing the bill. So this is actually a very practical question, and we'll answer that today. So here we go. Here was our confidence interval, 95% confidence. We sampled it at the sample proportion, which was what we had here. And we know the sample proportion is going to be within 2 standard deviations 95% of the time, or roughly 95% of the time. All right, so that means if it was within 2 standard deviations, then our margin of error, and we add that to both sides, it's going to successfully capture true proportion, whether it's on the high end or whether it's on the low end. It's still, our true proportion would be within it 95% of the time, and that's what we mean by 95% confidence. All right, so what if we wanted to decrease that to 5% confidence? So a margin of error, or not 5% confidence, 5% of a margin of error. So plus or minus 5% instead of plus or minus roughly 10%. So now we want our margin of error to be 5%. Our z-score is going to be how many standard deviations we go to the left and to the right for a certain level of confidence. For 95% confidence, we were saying 2, but it's actually 1.96. And then our standard error is going to be the square root of p hat times q hat divided by n. And those we're using its standard error because we're using our sample proportions instead of the true proportions because we don't know what they are. So I plug those in, and then n is going to be what we're solving for. That's the size of the sample we would need to have in order to have a margin of error plus or minus 5%. Okay, so what I'm going to do next is I'm going to divide both sides by 1.96. So I have all the square root by itself. When I do that, I can put that in the calculator if I want. So that's going to be 0.05 divided by 1.96, and that's going to give me basically this part here. And then if I want to undo a square root, I need to square both sides. So I'm going to take that value and I'm going to square it. And that's what this is going to be equal to. Now, there's a little trick that we can do here. We can actually take this value here and multiply both sides by n, and then divide them both by whatever that other value is here, so the 2.55% squared. So what I'm going to end up putting in the calculator at the very end, and if you want to put it as a fraction, you totally can. So if you hit alpha x, then it'll be alpha x. There we go. Let's try it again. Okay, so put it in as a fraction. Let me delete that part. And the numerator, I'm going to do 0.519 multiplied by 0.481. And then in the denominator, I'm going to do that previous answer squared, which is this thing that I got right there. So, oops, didn't want to do that. Let me see. See if I can do that again. All right, so I'm going to do alpha x to put it in as a fraction. And the numerator, we're going to do 0.519 times 0.481. Okay, and then the denominator, I'm going to put this answer here. So I'm going to do second a and s right down here, and that's going to put the previous answer in the denominator. All right, so that's going to tell me my sample size, which means I'm going to have a sample at least 384 CFANs. Now it's 0.6 CFANs, and in order to have 5%, I need to always round up. Even if this was like 0.2 or something like that, you always have to round it up to the nearest whole number. That'll give you slightly less than 5% instead of having slightly more than 5%. So basically, we're going to round everything up always to 384. Now, there is another thing, is that we're not exactly entirely sure what our proportion is going to be, and it could be closer to 50%. And if we remember on our law of diminishing returns, the worst case that we could have is if it was 50-50. That would give us the largest margin of error. So to get a more conservative estimate for the proper sample size, instead of using the sample proportions which we got from our sample, and remember at the beginning we wouldn't know if we were doing this before the study, which is typically what we'd be doing. So instead, if I estimated 50-50 for that, let me show you the math for that. It's the same thing, except at the beginning, let's do alpha x here. So I'm going to put it in as a fraction. This time I'm going to use 0.5 times 0.5, which is basically 0.25. And then in the denominator, I need to do this value squared. So I can't do previous answer because then that would give me this one. I don't want that one. So I'm just going to have to type it out and then square it. So 0.02555102. That's going to be precise enough. Then don't forget we're squaring that one. All right, and that's going to give me a slightly larger, more conservative estimate, worst case scenario of 50-50 for the largest standard deviation we could have, which would be basically 384.1, and even though this is 0.1, we still have to round it up, so that would be 385. So basically, if we use our sample proportions, we would say 384, but to be on the safe side, the worst case scenario we would have would be 385. Now these aren't that much of a difference because our sample proportion wasn't that far off from 50-50 in the first place. So that's basically the estimate. And then the next question we would have is we go back to our boss and we say, okay, well, are you going to give me, 2 weeks vacation to go snorkeling and scuba diving instead of 1 week's vacation? Huh? Sound good? But actually, if you think about it, with the law that we have here that we're dealing with here, this is an inverse square root. So what we're doing is as we're increasing the sample size, it's going to decrease the margin of error by the reciprocal square root. So if we want to basically cut our margin of error in half, like we did here from a margin of error of 10 to a margin of error of 5, then we'd actually have to do the reciprocal square root of that, which is going to be essentially multiplying our sample size by 4. So however long it took us to gather the 104, it's going to take us 4 times as long just to be able to cut our sample size in half. So that's kind of the reciprocal square root law that we're dealing with. By the way, that's the same law that you have with gravity. So the further you get away from the Earth or whatever the mass that's pulling you towards it, I could have made a joke about your mama having her own area code, but I didn't. See, I didn't do it because I'm mature. But anyway, whatever mass that you're trying to get further away from, it's the same reciprocal square root law, which is actually kind of cool. All right, so now let's review different types of bias, because there's some questions that are going to be here. So remember, when we're sampling, if we're not avoiding bias and doing random sampling, then and good data gathering methods, then we can't really trust the results in our confidence intervals anyway. So different types of bias. Bias is a failure of a sampling method that over or underrepresents a portion of the population. So anytime we have bias that's introduced to our sampling methods, then our samples are not going to be representative, and so it's basically just a bunch of junk, and you got to throw it out and try it again. So if I only sampled all the CFANs in one area, that would be considered like a convenient sample, and that would just tell me what's going on in that area, not what's going on in the whole reef and the Las Rosas Reef. All right, so voluntary response bias, this happens all the time. This is when you ask people to volunteer to be a part or offer their opinion instead of actually randomly sampling people. So if it's not randomly selecting people, but you're allowing everyone to volunteer for your poll, the people who are going to respond are the people who are interested in it or who have a very strong opinion about it, not necessarily everyone who'd be in the middle ground. So for instance, if we ask if like the Herd from Colin Cowherd or whatever, if he was asking who should be the mid-season NBA or MVP, it depends on who's following him. The only people who would vote are people who are following him. Let's say that he's very critical of, say he's, I guess, very critical of the Nets. Well, that wouldn't make sense. But in this case, very critical of Golden State. And so there's not a lot of people who follow him who are fans of Golden State. And so maybe that's why Steph Curry wasn't rated as high. But he's really big on the Clippers, apparently, or the Lakers or the Nets or something like that. So that would explain why those are so big. And this is obviously not from this season. That's not how that would work. Also, if you're on YouTube and you're watching cat videos and you put a poll in your cat videos and you ask people if they like prefer cats or dogs, you can't say that the people who respond to that poll are representative of all Americans because they're watching cat videos. Clearly, they're going to say that they prefer cats over dogs. So it's not a representative sample, and it's just a bunch of crap. All right, undercoverage bias is by leaving out a segment of the population in the sampling strategy. So if you mail out surveys, it's going to leave out anyone who doesn't have an address, so they didn't have a chance to respond. So don't claim them as a part of your results if you didn't actually sample them or include them in the population to be able to sample. So for instance, homeless people or people who are incarcerated that you couldn't mail out and to get their opinion, just don't claim them as a part of your results. Non-response bias. So when you have a bunch of people that don't respond to being randomly selected, so ideally you would have some sampling frame that matches your population, like voter registrations or some list of people that are potential list of people, or all the faculty or all the students or something like that with their student ID numbers. Then you'd randomly sample a simple random sample from that by assigning numbers and randomly selecting them. But if you have a lot of people that don't respond, then if their opinions are different than the people who do respond, then it's going to skew your results and you're going to have bias there. So what you need to try to do is track them down. So do the whole Liam Neeson from Taken thing. So I've got a certain set of skills that make me a nightmare for you. I will find you and do Liam Neeson things. Anyway, so track them down. Try to track them down. So if they don't answer, call back another time. If you're only calling during the day, you might have people who work during the day. You need to call them later at night or call them in the morning. Try to track them down because we need to know their opinion even if they don't answer. All right, so then convenience sampling. This happens quite often, like we discussed before. If we only sample the, I don't know, all 104 of the C fans that are in one area, that might be easy and we can get our sample size really quick, but it's not telling us what's going on in other areas. So don't do a convenient sample. Then my favorite one, the juicy one, is response bias. So response bias is actually a lot of things. It could be wording. It could be the situation the question that you're asking, if it's incriminating, like in this question. So if you were asked if you would hire somebody who has tattoos, visible tattoos, and you're asked by somebody who has visible tattoos, like this guy does on his neck, you're probably not going to tell him the truth, right? Especially because he looks like he could beat you up, and because you've been avoiding the gym, and you look like Captain America, but like the scrawny one before the operation, not the buff one afterwards. But anyway, so you probably lied to his face. So it's like, Anyway, also another question, if somebody asks you how fast you've driven, it depends on who you're asking the question. So if you're talking to your buddies, you might be honest and you might tell them how fast you've driven. But if a police officer asked you, you might not be so honest, or I don't know, officer, how fast was I going? It's ironic because right now my truck doesn't have a speedometer because I had to pull, it's got a parasitic draw on it, like a 0.4 amp drain on the battery, which kills the battery every 4 days. So I pulled the fuse that controls the cluster, which means I don't have like a fuel gauge. It also means I don't know my speed, which doesn't matter right now because I'm driving 25 really slow with the ice. But eventually It's going to be a really good or a terrible excuse. I have no idea how fast I was going, officer, because I don't have a speedometer. Anyway, I'll get it fixed. It's the radio electrical work. But anyway, kind of fun. So incriminating, no one's going to self-incriminate. If you ask them about drug use or alcohol use, or if they abuse or anything like that, they're probably not going to be honest to you unless it's going to be, what's the word I'm looking for? Anonymous, unless it's an anonymous survey, and then they might be honest. All right, so another example of response bias is how we word the survey. So I've showed you these before. They're infuriating, aren't they? So when the wording of the survey or question influences the way you respond from accurate or truthful responses, so telling people what they want to hear or oversimplifying issues. So these are an example of semantic overload. So when the words that we choose to represent certain things have multiple meanings to them. And what we really mean by these phrases, because these are phrases that as you read these, whether I read the one on the left or the one on the right, I actually agree with all those statements, and they all sound like, yeah, duh, of course, that sounds completely reasonable. But I don't agree with all the policies that go behind those statements. So these are loaded statements, and they're basically designed to belittle your opposition who disagrees with your political viewpoints of how you want to solve the issues, not whether or not there is an issue. So it's interesting. So these do frustrate me. Both of these signs frustrate me because I agree with all these statements, but I certainly don't agree with all the policies that these statements are representing. Let's put it that way. So response bias. It has to do with the wording of the questions. So a good one here is, so how would you rate the King's performance? Would you say he's doing a good job, an outstanding job, or a terrific job? I think I know who's paying for the poll, so they didn't give him the option to like not give him positive feedback, so it's kind of nice. All right, so when choosing a sample size, we want to set a certain margin of error or have a certain level of confidence and a certain level of margin of error, whatever the combination between those two are. So we have two different options. We can either decrease our level of confidence to have a smaller margin of error, or we can increase our sample size. And by increasing the sample size, it's going to be the reciprocal square root. So in order to half the margin of error, we'd have to quadruple the sample size. In order to cut the margin of error by a third, we'd have to multiply the sample size by 9. So just basically do the reciprocal and then square it, or square root it, however you want to look at it, from what direction you're going. All right, so let's go ahead and get started. 18 minutes, not too bad. Let's do example number 1. So in 1998, a San Diego reproductive clinic reported 49 births to 207 women under the age of 40 who had previously been unable to conceive. So check your conditions. Do you think it's appropriate to make a confidence interval? So basically, there were 207 women within the whole year that went to the San Diego Reproductive Clinic and sought fertility treatment. And of those 207 who did the treatment, which is rather expensive, 49 of them were successful in conceiving and delivered live births, which is wonderful. But that also means that the other ladies had complications and were unable to conceive, or unfortunately, their pregnancies were not successful, which is really sad. I know, really sad. Moment of silence. All right, so plausible independence. So the question we have is, are these women related? So if one woman has success, is that making another woman more likely to have a success? Well, as long as they're not related to each other, like if you had twins or something, then you would expect them to have similar medical, I don't know, things. And so if one of the twins was successful, then maybe the other one would be more likely to be successful as well. So, but it is plausible to believe that each woman's should respond to the treatment independent of another woman. So we should be okay with that one. Randomless sampling condition. So this was not a random sample. In fact, this was a census. Because we have information about all 207 women from 1998 who visited the San Diego reproductive clinic and sought treatment. So there's no reason to really sample in this case. So it's not a random sample, but a census of all of them, which is actually okay. Could come into play and kind of be an issue with the 10% condition though, because but the question is, what is our population of interest? Are we only interested in the 207 women who came in 1998, or is our population of interest all women who might seek fertility treatment? And in that case, our population is much larger. The 207 are just the ones that actually came in. So they are volunteers in this case, but that should be okay as long as we believe they would be representative of all the other women who might have come in. But that might not be true, because maybe the only ones who sought treatment were the ones who had a minor issue or something. I don't know. I've never been a woman who's had issues conceiving. Whatever. All right, so 10% condition. It should be less than 10% of all women who may seek fertility treatment, so we're okay. Success failure condition, did we have at least 10 successes and 10 failures? So yes, we had 49 successful pregnancies, so that's more than 10, so we're good. And on the other side, unfortunately, for those women, it's really sad. I'm sorry. All right, find a 90% confidence interval for the success rate at the clinic. So to do that, I'm going to go back here where my data is and go to stat, arrow over to test, 1 proportion z interval. They said 90% confidence, and we had 49 out of 207. Okay, hit calculate. So that's going to be between 18.8 and 28.5%. All right, so basically that's our confidence interval. So we would interpret that as saying we're 90% confident that the true proportion of women who would be have successful treatment and fertility would be between 18.8% and 28.5%. Okay, correct. All right, D, explain what 90% confidence means. That means 90% of all of our samples of 207 would successfully capture the true proportion. So 90% of the, or in other words, we expect the true proportion to be within the margin of error of the sample for 90% of samples of 207 women. Does this data refute the data's claim that 25%? All right, so they are claiming 25% of women will find success in their treatment. Well, if we look back at our confidence interval, is 25% contained in our confidence interval? It is, so it is reasonable to believe that that is a potential value for the true proportion. So it might be true that the true proportion is 25%. Now, no one actually knows what that true proportion is, so I don't know how they could claim such a thing, but we don't have enough evidence to call BS on their claim, because it was actually 25% was actually contained within our confidence interval. So it is possible, we believe, that the true proportion could be 25%. Number 20, local news. A mayor of a small city has suggested that the state locate a new prison there, arguing that the construction project and resulting jobs will be good for the local economy. A total of 183 residents show up for the public hearing on the proposal, and a show of hands finds that only 31 in favor of the prison project. What should the city council conclude about the public support for the mayor's initiative? All right, so if I created a 95% confidence interval, 31 out of that, and put it in the calculator, this is the 95% confidence interval that I would get. But before you just go straight to that and then conclude, oh, well, that's not more than 50% because it's not contained in the confidence interval, so obviously we don't have a majority support. Excuse me, then we actually first need to go through our conditions, because this one's going to violate a bunch of conditions. So what should we conclude? Well, who goes to the public hearings? Is this a random sample? Should we expect that this sample of people that we did, the 183 residents that showed up, are they representative of all the people and all the people's opinions? Or are they all a part of a certain interest group that something, or are these only people who have really strong opinions, but what about all the opinions of the everyday Americans who are more middle ground or could be care less? I don't know. But not everyone's going to show up, and so this is not a representative sample. So we can't conclude anything because we can't expect it to be a representative sample. There was no attempt of randomization in this at all. So we've got a few types of biases here. So response bias. One is that you got social pressure. So if it seems like there were 31 brave people who raised their hands, well, maybe there were other people who wanted to raise their hands, but they were next to somebody who was violently against it and they didn't get beat up or something like that, right? Because unfortunately, tensions, pressure, right? You all feel it, right? So maybe people weren't willing to raise their hand, but if they took a secret ballot or a vote or something like that, then you would have actually seen the true proportions. In fact, our Senate and our House does do secret ballots, and it's kind of funny because publicly they'll show support for something, but then when they do a secret ballot, they stab people in the back behind the back. It's awesome. Anyway. So next one is voluntary response bias. So the people who we are sampling, we didn't randomly select them. We allowed them to volunteer for it. So this is not random sampling. It's not a simple random sample, so they weren't randomly selected. So we shouldn't expect them to represent everyone else. They are volunteers. So this is voluntary response bias. Again, only the people with the strongest opinions are going to show up, whether for or against, and all the people in the middle ground probably going to have something better to do with their Tuesday nights. But their opinions still matter. And right. All right, so convenient sample. So again, this would be an easy way to do it. They already showed up. These are, we'll just raise your hand, all right? Well, it's not the best way to collect the data. You've got response bias. Raising your hand might mean you get beat up later, especially scrawny arms and stuff like me. So it's probably not the best way to do it. It needs to be anonymous and lots of different issues with it, but no effort for random selection, so it's not going to be a representative sample. All right, 30, hiring. In preparing a report on the economy, we need to estimate the percentage of businesses that plan to hire additional employees in the next 60 days. Okay, so we want to estimate the proportion of businesses in our local area or whatever that are planning on hiring somebody in the next 60 days so that we can publish this in a newspaper or whatever we're trying to do. So how many randomly selected employers must we contact in order to create an estimate which we're 98% confident with a margin of error of 5%? So we're setting our margin of error 5%, which is this part here, and then our z-score to find that for 98%. That's not one of the common ones that we do, but we can find it if you remember by doing the inverse normal. So I'm going to go to second, distributions, inverse normal. The area we're going to do under the curve is going to be 0.98, 0 and 1 because we're doing z-scores for the standard normal, and measuring the 98% from the center. All right, so that's going to give us critical values of 2.326, which is what I have here. Okay, so, and if you forget the critical values for any of these, you can just do the inverse normal to find it again. All right, so 5% margin of error, critical value for our confidence level of 98%, and then we don't know, we don't have any idea what the level a p hat or q hat is going to be in this case. So we're going to do our most conservative estimate, which is always 50-50 anyway. So I'm going to do 0.5 and 0.5. If you have a sample already, you can use those values, but it's often better just to use 0.5, 0.5 for the basically worst case scenario. Okay. To err on the safe side is what I'm trying to do. All right, so what we're going to do is divide both sides by that value. So in the calculator, that's going to be 0.05 divided by 2.326, okay? And that's where I get this value. And then to get rid of the square root, I want to square both sides. So I'm going to take that value and square it. All right, and then now I want to switch the order of these two. So pretty simple, just dividing both sides and multiplying both sides by n. So what I'm going to end up putting in the calculator is going to be, and I'll do it as a fraction so you can see it. So alpha x on the top, 0.5 times 0.5, which is basically 0.25. Just save you some time. Divided by the previous answer, which can be that value right there, because that was this thing squared, right? All right, so that's going to tell me I need a sample size of at least 541.02. But even though it's 0.02, I always have to round it up. So basically 542. And that'll guarantee that I have at least a margin of error of no more than 5%. All right, so I think that's all we have to do on that one. So, okay. Suppose we want to reduce the margin of error to 3%. All right, so same thing, but now it's 3%. Well, it's really the same math. We just got to now start over, so 0.03. Divide it by the 2.326. Okay, so that's how I got this value. Just divided both by that. Then square it. So take that value and square it. And then switch those two. So it's going to be, I'll do it as a fraction for you. So 0.25 divided by the previous answers. So second ANS. I did square that, right? Okay, cool. Yeah. So now, whoa, we got to have 1,503. That's a big difference, right? Okay, so what happened? Well, I can actually go back. So if I'm going from 5% to 3%, remember it's the reciprocal square root. So I'm going to go back to this one here and actually show you kind of a shortcut, which is fascinating. All right, so from this value, if I want to go from 5% to 3%, so I'm going to flip it and I'm going to multiply it by basically 5 squared, which is 25, divided by 3 squared, which is 9. And magically, you ready for it? Boom. See how I got exactly the same thing there? Awesome. Okay, so the reason I divide it by multiply it by 25 and divide it by the 9, because 3% is what I'm trying to go to, and then I'm starting at the 5%, and it's got to get bigger, so it is the reciprocal. So it just hurts your brain. But if you can think about it, if we're going from 3 to 5, it's like 3/5, but then we're squaring it and doing the reciprocal, so it's 5/3. 5/3 squared is 25 over 9. So if you can follow that, good for you. If not, don't worry about it. Just do the math again. It's not that big of a deal. All right, why might it not be worth it to try to get a interval with a margin of error of 1%? Well, if to 1/3 the margin of error from our previous value, right, we would have to basically do the reciprocal square of that, or reciprocal square root, but we're going the other way, so we're squaring it, which means it would be 9 times the previous one. So that times 9, which would mean, yeah, that's huge. So we would need to multiply the sample size by 9. So we would have to sample basically 13,526 people in order for us to have a margin of error of 1%. Now think about it, plus or minus 1%, we've really, really, really narrowed it down to pretty much the true proportion. So at this point, with such a large sample, you start getting into violating the 10% condition. So if our true proportion or true population is more than 135,000, then we're okay, but then otherwise we're going to get to some issues. So it's just the cost is going to go up a lot. So as we narrow down our margin of error, when keeping the confidence level the same, our cost is going to go up for our sampling. All right, part D. Others of the business are willing to report and accept a margin of error of 4%, but they want 99% confidence. How many randomly selected employers will they need to contact? So we change our confidence level to 99%, so our critical value is now going to be 2.58, and then we have 4% margin of error. So on this one, we're going to put it in the calculator. So 0.04, we're going to divide both sides by 2.58, and then we're going to end up squaring it, and then we're going to do our most conservative estimate, which would be 0.5 times 0.5, which is 0.25, divided by the previous answer, and that's going to give us a rough conservative estimate of 1,041. Remember, we always round it up. So they would need to randomly select 1,041 employees to be able to do that. All right, 36. TV news reporter says proposed constitutional amendment is likely to win approval in the upcoming election because a poll of that many voters indicated that 52% would vote in favor. The reporter goes on to say the margin of error for the poll is 3%. So he should, whenever he states the sample proportion, he should always say plus or minus the margin of error. So if they don't tell you that, then they're kind of being a little bit deceptive. So you shouldn't later have to read several paragraphs before they tell you the margin of error. It should be 52% plus or minus 3%. But people don't know how to interpret stats anyway, but you do. Yeah, see, it's very important. You do. All right, so why is the polling actually inconclusive? Well, because 50%, which would mean the majority of support is 50%, is within the margin of error. So we're 90% confident, or they don't tell us the confidence level. They should always do that too, by the way. We're 90 or 95% confident, or whatever we are, that the true proportion is anywhere between 49 and 55%. But because it could be 49%, it's inconclusive. So we don't know if it's whether or not we're going to actually have enough, whether or not it's going to pass or whatever. And so, especially during the election, you hear that quite a bit, that the difference was, it was really close or whatever, and so it was within the margin of error. That's what they're talking about here. So we had to wait until the actual election day to figure out what it was. All right, so what confidence level did the pollsters use? So on this one, margin of error was 3%. Confidence level is going to be coming from our critical value. And then we can use these, the actual values that we had here. So 0.52 and 0.48, which is what they would have used because they had that 52%. And all we really have to do on this one is basically just divide both sides by that value, whatever that standard error is going to be. So kind of a mess to put it in the calculator, but not that bad. So I'm going to do the margin of error first, or sorry, the standard deviation first. So that value times 0.48 all divided by 1505. And then I'm going to take the square root of it. Oops, didn't mean to do that. So caret 0.5. Okay, and then I'm going to do 0.03 divided by that answer. So 0.03 divided by previous answer. And that's going to give me 2.32 0.29. So basically that was our critical value here. Now to find that doesn't match any of these values we have. So they didn't use a typical confidence interval. So to find out the range under the curve for that, I just do the normal CDF. So second distribution, normal CDF. And my lower limit's going to be that z-score, so 2.3295. Upper limit, the positive version, 3295. Standard normal, so 0 and 1, which is 98% confidence. So they use a 98% confidence level. All right, so that is the last one that I'm going to do with you. Sorry it went a little bit long today. I'll see if I can trim some of that stuff out. But anyway, if you have any questions, please let me know. The next one we'll be doing is a review.